Good afternoon, good evening, ladies and gentlemen. We're going to be talking about standard enthalpies of formation today, which have a symbol of delta H sub F. That sub F is telling us formation. We're making things like compounds. And we have a compound. This is going to be the change of enthalpy, the change in heat at a constant pressure that accompanies the formation of 1 mole. It's a very important idea, 1 mole of a compound from its element with all substances being in their standard state. That's a big mouthful, and it'll make sense once we talk about it here. So essentially, let's define what standard state is first. Standard state is going to be our delta H, and this little 0 right there tells us that something is at its standard state. Now, standard state is going to be 1 atmosphere. It's going to be 25 degrees Celsius, which we also call room temperature. And it's also 1 molar if we're dealing with solutions. The delta H value for elements that are at 1 atmosphere, 25 degrees Celsius, is going to be equal to 0, as we're going to see later. We like to say these are just standard states. So like if we were, let's say, hydrogen gas at 1 atmosphere, 25 degrees, we would expect it to be a gas. And so the enthalpy would be 0. Iron, solid iron, room temperature 25 degrees Celsius, 1 atmosphere, we would expect it to be a solid. So the delta H standard is going to be equal to 0 as well. And it'll be different for different compounds. Let's talk about here the formation of nitrogen dioxide. If we take a half of mole of nitrogen, reacting it with 1 mole of oxygen, we're going to form some nitrogen dioxide. Now, up above, we talked about it forming 1 mole for the formation, delta H of formation. This equation, as we remember we learned in regular chemistry, we can never have a fraction as a coefficient. The reason we can have a fraction as a coefficient here is because we're forming just 1 mole. And if we had this coefficient as a 2 or a 1 or 3 or whatever, it would not form just 1 mole here. So that's why we have to have a half a mole there. The delta H value for this is positive 34 kilojoules per mole. Tells us that this guy is going to be an endothermic reaction. It's going to absorb heat to make this reaction occur. Now, if any problems we were asked to calculate delta H formation standard state and we don't have these values, like some homework problems we're going to do tonight, we can just look them up in Appendix C in the back of our white book. It's just way at the back. There's a couple different appendices. Look there if you don't have the values given to you. But there's a formula that we're going to use to calculate delta H, or enthalpies of formation, at standard state. And this is the formula here. And let's talk about what this all means. So we have delta H of reaction, standard state. This just means the sum. N here is telling us the moles, which we're going to multiply by each delta H for the products. Then we're going to subtract the sum, again, the moles multiplied for delta H of the reactants. Now, that seems kind of complicated, and it's not. Let's set up a problem and talk about it here. So we have thermite reaction. This is a fun reaction to do, and I do have a little bit of thermite, and I'll show you this reaction, not necessarily tomorrow, but I will show you some thermite. And this is thermite. Thermite is taking aluminum in a solid form and mixing with iron 3 oxide, which is essentially just rust. So we have some aluminum powder and some rust, and we mix them together, and they're really hard to get reacting, but once you get the reaction energy going strong enough, this reaction occurs, you form aluminum oxide, and you also form iron. And this iron will come out in a liquid form but then solidify really, really quickly. And we're going to be asked to calculate delta H of this reaction. So I'm going to be looking up some values in the back of the book. Now, the formula that we're going to use again is going to be the sum of the moles, delta H of formation of the products, minus the sum of delta H formation of the reactants. So it's basically products minus reactants, and we're going to throw in the coefficients there as well. So I'm going to go to the back of the book and I'm going to look up some values. So I'm basically looking at my delta H formation standard state for each one of my reactants and products. For Fe2O3 in the solid form, I'm going to get a value of negative 826 kilojoules per mole from the back of the book. I look up aluminum oxide solid in the back of the book, which is one of my products. That's going to be negative 1676 kilojoules per mole. Also, I look up in the back of the book my aluminum solid and my iron solid, and those guys both turn out to have a delta H formation of 0, and that's just because that's what's expected at their standard state. Aluminum is a solid and iron is a solid, so it's going to be real easy. We're just going to plug in 0 there. So essentially what we're going to do here, let me kind of scooch this back down a little bit, is once again we're going to do products. So we're going to do the sum of our products, which we have just one aluminum aluminum oxide, and so that's going to be negative 1676. Now, up here in the balanced equation, there is only one of these guys, so I don't have to multiply a coefficient through here. And then I'm going to, because it's the sum, I'm going to be adding in my iron here, and I have 2 of them, but iron is 0, so it's basically 2 times 0 is 0. So that's for the iron. So once again, this is Al2O3, and this is our Fe. Okay? And we're going to take the sum of those 2 guys, and then we're going to subtract out the sum of our reactants. And our reactants are going to be 2 aluminums, so it's going to be 2 times 0. And then we're going to add that to Fe2O3, which we only have one of those guys, so this is going to be negative 826 kilojoules per mole, and this is obviously 0. So all I have to do is do this mathematical operation, and so it's essentially negative 1676 minus a negative 826, and I should come up with negative 850 kilojoules as an answer. And that negative sign there tells us that this is a very exothermic reaction. As a matter of fact, it's so exothermic, it gives off so much heat that it actually melts our solid iron up here into a liquid form, and which is kind of neat because we can form liquid iron. And that's essentially how we do enthalpies of formation. Just a couple things, we didn't really get into it, but let's kind of just go back into this equation here. And for our 826, this was for our Fe2O3, which in the balanced equation, looking up here, we had a coefficient of 1. Now, if we did have a coefficient, let's say we had a coefficient here of 2, what that would change down here is we would have to multiply this value by 2. But we didn't, so I'm just using that as an example. So you'll see in some homework assignments tonight, you do actually have to change, you have to multiply that coefficient through. That's tonight's homework, and you will have some couple problems to do. Look on Edmodo.